Hello and welcome to the lecture 2B of the Computer Architecture and Microprocessor System course. Here we'll be looking at combinational logic design. I think in the last lecture we looked at how to use transistors to build individual logic gates like the AND gate, the OR gate, the XOR gate, and gates like that. Now we'll be using those AND gates, XOR gates, and OR gates to build larger digital circuit components. And then this is what in digital systems is known as the combinational logic design. Now here, the big picture again is that at the end of the entire course, we'll be building a circuit like a simple CPU, which is single cycle like this, and then we have to know how the individual components of this CPU is built before we can begin to build it. And then one of the components that are used in the single cycle processor combination logic, each and every component, the memory, the register file, the ALU, is made up of logic gates. So you will see how to combine these logic gates to build components that will be used in our single cycle processor. Now these are the basic logic gates we need to know, and then we need to know in order to be able to build combinational logic blocks. We have the buffer with this truth table. We have the AND gate, OR gate, XOR gate, an inverter or a NOT gate, an AND gate, a NOR gate, and an exclusive NOR gate. So these are the gates we'll be using to build combinational logic blocks. Now, combinational logic is often grouped. In combinational logic, we often group logic gates, individual logic gates, into larger building blocks that are used in very complex systems. Right now, the combinational logic block always hide the abstraction or the lowest abstraction, which is the logic gate, from the person building it. And then here we are going to examine combinational logic blocks that are used to build data system components like decoders, multiplexers, a full adder, and then a programmable logic array, the PLA. We will also be looking at, I think, a priority encoder and other components like the tri-state buffer. So we start off with a decoder. So what is a decoder? A decoder is simply an input pattern detector, right? So you have a series of, or you have inputs, and then you need a circuit that will be able to determine the pattern. That will be able to choose or to activate the output based on a particular input pattern. So that's what is known as a decoder. Now the decoder has n inputs, and anytime a decoder has n inputs, anytime a decoder has n inputs, the output of the decoder will be 2 raised to the power n. So if you have a decoder with 4 inputs, the output will be um, 2 to the power 4, which equals 16 outputs, right? So that's how to find, for instance, you're given the output of a decoder, a decoder has 16 outputs. How many inputs whose will be able to address those 16 outputs? So it is simply 2 to the power n outputs is equals to n inputs. Now, exactly one of the inputs is actually selected at the time. So if you have a 4 input decoder and then we have 16 outputs, only one output is actually always selected at a particular time. Right. So if you take an example of a 2 by 4 decoder, this is digital system. Anytime you are given a design, you always start off with a truth table in order to understand what the design is about. So once we take a 2 by 4 decoder, it means that we have two inputs. It means that we have two inputs, A1 and A0, and then to address two inputs, we need just 2 bits to address it. And then we have 4 outputs, Y3, Y2, Y1, and then Y0. So in this configuration or in this truth table, what you can see is that when input A1 and A0 above 0, only Y0 is activated. So as I said, the decoder makes sure that only one output is activated at the time. So when we have, if the input A1 is 1 and A0 is 1, only Y3 is activated, all the rest are deactivated, right? Now the symbol for the decoder is simply this. So anytime you see a circuit, a symbol like this is a 2x4 decoder. Now, essentially, what is inside the decoder? So how do we said that we are using logic gates to build larger components like combinational logic. So how do we actually uh, build or use those logic gates to build the decoder? So first of all, what logic gates will be used to build the decoder? We have to first of all look at the truth table of the decoder. Now, whenever an output, whenever an input, an output, only one output is activated at a time. So to build this logic, to use logic gates to build this decoder, you have to first of all start it off like this. Now let's start off with Y0, right? So Y0, then this is our output Y0. Now Y0 is 1. When A1 is 0 and A0 is 1. So we have our input A1 and A0. We are going to build this with an AND gate. And then we said whenever our A1 is 1 and A0 is 1. So we need an inverter here and then an inverter here to the AND gate. And then this will simply address Y0. So when A0, A1 is 0 here and then A0 is 0 here, the output of the inverter will be 1 here, the output of the inverter will be 1, and then the output of the AND gate will be 1. So A1 will be 1. So that is how you simply build the output Y0 with an AND gate and an inverter. So to make this easier, or to make the diagram easier to draw, once an input to an AND gate is an inverter, we just put a circle here and draw a line to the input. A circle here, and then I draw a line to the input. This indicates that this is an inverter. There's an inverter connected to the input of the AND gate. Now we move on to Y1. So this is Y0, so Y1. So Y1 in the same one, A1 is 0 here, A1 is 0, A0 is 1. So we have an AND gate, we have A1 and A0. So A1 is 0, so you put an inverter here, right? And then A1 is 1, so no inverter here. And then this will be connected to our Y1, right? So that is just how you build it. And then for Y2, again you have your AND gate. A1 is 1, so you have A1, and then A0 is 0, so you have your inverter here. Connect this and connect that, and then this is connected to the output. And then you have your Y3 here, another AND gate. For Y3, A1 is 1, no inverter. A0 is 1, no inverter. So A0, A1, A0, and then this is connected to your output. So this is the logic. This is how you use logic gates, logic gates to build your decoder. So here we have two logic gates involved. We have an AND gate and then an inverter or a NOT gate. So we have used two gates to be able to implement our decoder. So now this is just what I just explained about how to build the decoder using logic gates like the inverter and then the AND gate. Right? So you can trace and pass inputs to your design or to your circuit, and then look at the output to see whether it matches with the truth table. So now, what is the use of a decoder in digital systems? Now, first of all, a decoder can be used as an address locator. Now, once you have your memory, if normally we have memories in digital system, we have memories, right? And then the memories are always organized in this form, right? We have addresses, we have the data wave of the memory. This is what we call the data wave of the memory. And then we have the depth of the memory. The depth just indicates how many locations are within the memory. Now, to address the locations within the memory, we have what is called the memory address. So this particular portion of the memory will be if you want to read a value from this location, we have to give it an address. And then let's say we have here to be address 0, 1, 2, 3, 4, 5, 6. So these are the addresses, memory address. So in order to read for memory location 6, all of these portions of the memory have to be deactivated, and then we read from only memory location 6. So once we know the operation of a decoder, this has 1, 2, 3, 4, 5, 6, 7 outputs, right? So we have a 7 by, now we said 2 to the power n output is equals to n input, right? So to address these 7 memory locations, we need at least I think 3 bits to address this particular memory. So now we have to connect the output of this decoder to the address locations of the memory. And then if we want to for instance, select or read a value, read or write a value from memory location 1, we have data inside our memories: D0, D1, D2, D3, D4, D5, and D6. So anytime we want to read from memory location D0, we have to give the input 0, 0, 0, and then it will activate only this line. And then all of the other lines will be 0, 0, 0, 0, 0, 0. And only one will be activated, and then you can actually read or write with the memory. So that is one use of the decoder. This is a very, very important use of the decoder for activating addresses in memory to read and write from. Another use of the decoder is that it can be used within the processor to actually decode instructions. Now, when we looked in the first lecture, we looked at the machine language. And then we said that for machine language, it consists of zeros, 0, 0, 0, 0, 1, 1, 1. It's either 0 or 1. And then we have a portion of the machine code that is known as the opcode. Right. So now this opcode actually determines what the instruction is about. So this series of 1s and 0 in the machine code is what is called the instructions. And then this portion of the opcode will determine what instruction the CPU is supposed to execute. So we could have a number of instructions here. We could have add immediate, add I. We could add registers. Add I just means that we are adding a register value to an immediate value or a direct numerical number. Add just means that we are adding two registers, the values, the contents of two registers. You could have multiply, you could have division, you could have exclusive or, you could have and, you could have and, you could have or. So many functionalities which this opcode um, which this opcode tells us about. So a decoder could be, you could design a decoder to indicate each of the operations. So the decoder could be outputs that outputs and or, add I, add, multiply, division, and so on. So what the decoder does is that as long as it sees the inputs of the input comes as the opcode. So as long as it sees the value of the opcode, the decoder will actually decode and activate one of these functionalities, add or XOR or whatever functionality it is. So this is another use of the decoder. Now we move on to our second combinational block or component, which is the multiplexer. So what is a multiplexer? The multiplexer actually selects one of n inputs to connect it to the output. So you have n outputs. So you have n outputs, a series of outputs from 0 to n, and then the decoder selects just one of the outputs, and connects it to one of the inputs and connects it to the output. So this is the output, and then this is the input. So the decoder always has one output and a number of inputs. One output, a number of inputs. And then the most important thing is that the decoder always has what is known as the select line. Right. So now how do we choose one of the outputs to be assigned, one of the inputs to be assigned to the output? We need what is called the select line. And then the select line will choose one of the outputs, one of the inputs, and assign it to the output. Now, how many bits are needed to address the select line? Here again, just the same thing. 2 to the power n inputs. 2 to the power n inputs is equals to n select lines. Right. So if you have a select line which is 4 bit, if you have a select line which is about 3 bits, so it means that our outputs will be 2 to the power 3. Our inputs will be 2 to the power 3, which is equals to what, 8. So you have a select bit of 3, our inputs will be 8. Right. So here, this 3 bit will have to select one of the 8 inputs and then assign it to the output. So that is what a multiplexer is. And then we take a simple example, which is a 2 by 4 multiplexer, a 2 to 1 multiplexer, simply a mux. So here, what simply happens is that we have two inputs, D1 and D0, and then we have one output, which is Y. Now here, as it can be seen, S is a select line. So the X will actually activate, or the X will make sure that only one output is sent, only one input is sent to the output. So if S is 0 here, you can observe that the output Y here is 0, 1, 0, 1. And then once you check the input, you see that 0, 1, 0, 1 is D0. So as long as S is a 0, as long as S is a 0, the input D0 will be routed to the output. Now if S is 1, 1, 1, 1, if S is 1, you can see that the output is 0, 0, 1, 1. And then once we look through the outputs, once we look through the inputs, you see that D1 is 0, 0, 1, 1. So as long as S is 1, the input D1 will be routed to the output. So this is how um, the multiplexer works. And then this is the symbol of the multiplexer. We have S to be the select D0, D1 input. We have a 0 here, 1 here. It just means that if S is 0, D0 will be routed. If S is 1, D1 will be routed to the output. Right. So now let's see how are we going to simply design what is inside the multiplexer. So how do we design or use the individual logic gate, AND gate, OR gate, XOR gate, whatever gate is available to design a simple multiplexer? Now we have to actually be observant of the truth table. We have to look at the truth table in order to be able to draw our logic gates, and then or to be able to properly combine our logic gates to mimic that of the multiplexer. So now you have to first of all look at the input in relation to the output. Now when we come here, as long as S is 0 here, we see that the input D0 will be routed to the output. So if S is 0, D0 will be given to the output. So here you can have a very, very simple AND gate. Then we connect our S here to an inverter, and then we connect our D1, right? And then this will be Y. So what this simply means is that if S is 0 here, the output of the inverter will be 1, and then D1 will be routed to the output. That is what it simply means. Now, yet again, we have another, we have D0 to also look at. So as long as D0 is 1, the output, the input, as long as D0, okay, sorry, this is for D0. So S and D0, right? So if S is 0 here, the output of the inverter will be a 1, and then D0 will be routed. That's not instead of D1, right? So now we have to look at D1 again. If S is 1, if S is 1 here, if S is 1, D1 will be routed. So again, we have our S here. Here, because we are using, because S is 1, there's no inverter. So S is 1. And then we have our D1 here. And then the output will be routed. Right. So now this output Y and the output Y are the same. So we need another logic gate to connect to these two. So here we can just simply use an OR gate. Connect these two here, and then you have a Y here, right? And then yet again, this S and then this S is the same, so we can connect them together. So we have our S here, right? So this is the simple circuit of what a multiplexer is. Now here we can pass the inputs through the truth table to see what we get. So as long as here, if S is 0, we see that this AND gate, the input here will be 0. So the output here will be automatically 0. Now if here is 0, the input to this the output to this inverter here will be 1, and then D0 will be routed through here. And then once we have an OR gate, and then we have one of the inputs to be a 0, the output would depend on the other input. So D0 will be routed here. So this is a simple design of a multiplexer. So here we have used 3 logic gates to design our multiplexer. We have our OR gate, we have our AND gate, and then we have our NOT gate of our inverter. So we've used 3 logic gates to be able to design the multiplexer. Now we can use the multiplexer to design um, other circuits like the lookup table. We looked at the, the lookup table in the first lecture. So you'll see how we'll be able to use the multiplexer to design what is known as a lookup table. Or we can also use the multiplexer to design but we first of all have to look at how do we use the multiplexer to design the logic gates. Now we've been able to use the logic gates, the AND gates, the OR gates, and whatever to design the multiplexer. But we can also use a multiplexer to also design or to also mimic or to also mimic the logic gates. So for instance, here is a truth table of an AND gate. We know that in an AND gate, as long as one of the one of the inputs is a 0, the output is automatically a 0, unless both inputs are 1. So that is the truth table. So what we can do to this, what we can do here is that we can have a multiplexer that has 2 inputs, A and B, and then the input A 0 0 0 1 and 1 0 will be grounded. So we ground 0 0 0 1 and 1 0, and then we connect um, the input 1 1 to a power source, right? So that's what has been done here, and then we have an output. So here, as long as A is 0 0 2 1 0, the output will be a 0 because those inputs are connected to the ground. And then as long as A and B is 1 1, the output will be a 1. So this is how we've been able to use a very simple multiplexer to design an AND gate. Right now, here we can actually simplify this further in order to use less inputs. Now, once we observe the truth table of an AND gate, here, if A is, as long as A is 0, the output is a 0, right? So you can see that as long as A is 0, the output of the AND gate is a 0, and as long as A is 1, the output of the output of the AND gate is the input of the AND gate, right? So if A is 1 1 here, you see that B is 0 1, and then the value of the output is 0 1. So as long as we can draw another truth table to have only A and Y, as long as A is 0, the output is 0, and then as long as A is 1, the output is B. And then here we can use A as our select to the multiplexer. We ground the output, we ground the input 0, and then we connect B to one of the inputs, and then we have our Y. So if A is 0, the grounded value will be routed to Y, which is 0, and if A is 1, B will be routed to Y, which will be B, right? We can use the multiplexer to actually mimic a lot of logic gates. So you can do or go through it on your own in your free time. Now let's look at the programmable logic array. a very, very important combinational logic in this course. Because you've already treated digital systems, I'm not going to go a lot deeper into this, but you have to know that, or you already know that we have what is known as the sum of products. The sum of products in logic gates will lead to a two-level logic. Once you have a sum of product, you have the sum, which is an OR gate, and then we have the product, which uses AND gates. So the sum of product leads to a two kind of level logic. One side will be AND gates, and then the other side will be OR gates. So if we take an example like this, y is equals to this equation. This is the a Boolean equation. You can see that anytime you see a dot, the dot represent the product, and then the plus represent the sum. So this is a typical sum of product equation, and then we can design this sum of product equation using AND gate and an OR gate. Now you have the first level. Now how do we design or how do we implement this equation using gates? So first of all, we have y, which is our output, is equals to a bar, b bar, c bar. So we can have an AND gate here. So this is a, b, c, right? So that is for a bar, b bar, c bar. We have another AND gate for a, b bar, c bar, a, b bar, c bar, and then we have a, b bar, c here. A, b bar. Okay, this one is a, b, and then c bar. So we have another note here. So this is a, b bar, note here, and then a c. All right. So now these three outputs of the AND gates will have to feed into an OR gate. So we have an OR gate here. And then we have our y. So this is a simple representation of the sum of products. We have two levels here. We have one level will be the AND gate, and then another level will be the OR gate. So that is how the PLAs just work. The programmable logical ways, they use the sum of products, and then they're actually very easy to implement. Right now, the sum of products or the PLA can be used to actually design any logic or any logic function we want. And then the first thing we need to note is that it consists of an array of AND gates followed by an array of OR gates. As we can see in the diagram here, we have an array of AND gates and then also followed by an array of OR gates. Now, how do we determine the number of AND gates to use, right? And then this can simply be determined using the sum of products. So if you're given an equation, you'll be able to know from the sum of products how many AND gates you will want to use. And then those number of AND gates would depend on the number of inputs that you have. So for instance, if you have an n, if you have an n input, if you have a design with n inputs, the number of AND gates you use to be 2 to the power n. So here I have my input is a, b, c. We have three inputs. So you have a, b, c as input, which is 3. So we have 2 to the power n, which equals 2 to the power 3. So we have to use a total of 8 AND gates, right? So those are the number of possible AND gates you can use. And then you have to also know how many OR gates to use. So how do you determine the number of OR gates? Now, once you look through your truth table, as I said, in data solution, everything will have to be done with the truth table. You look through your truth table and look at the number of outputs from your truth table, and then those will be the number of OR gates to use. So the number of outputs in your truth table will actually determine your outputs. So which is is just directly proportional. If you have three outputs in your truth table, it will be three outputs. Now again, if you look through your truth table and then the number of inputs in your truth table, you have to just raise it to the power. So if you have four inputs in your truth table, you have 2 to the power 4 total number of AND gates, right? Now, how do we implement any function using the PLA? All we have to do is that the PLA shown in this diagram, we have the inputs that are connected to all the AND gates, and then we have the output of the AND gates are all connected to the OR gates, and then we have the outputs of the OR gates coming out. Now, to implement a function using the PLA, you have to connect or disconnect some of the inputs to the OR gate, which are outputs of the AND gate. So you have to connect or disconnect it, and that's what is termed as programming um, the PLA. And then that is, I think, in digital design, that is just what programming is. You are connecting some components and disconnecting some components, and then that's how logic functions can be designed using the PLA. And then that is how our FPGAs actually work. So the PLA consists of an array of AND gates, as I said already, and then an array of OR gates here. Now we actually connect the outputs of the AND gates to the inputs of the OR gate, and that is how a function can easily be implemented. Right, so now let's see how we can implement if you have a system like this, which is the PLA. How do we use this kind of design to implement a simple full adder? So this is the truth table of the full adder. We have input A, input B, and then we have the carry in, right? And then the output is, we have two outputs in a full adder. We have the carry and then the sum. So S is the sum, and then we have the carry. So if the value, if A is 0, B is 0, the carry in is 0, we already know that for a full adder, the sum is 0, and then the carry is 0. Now, if you have, for instance, the last instance here, if you have A to be 1, the input A to be 1, B to be 1, the carry in to be 1, we know that in the full order, 1 plus 1 plus 1 is 3. 3 means that the sum is 1, remainder 1. So we have 1 here, and then the carry, which is 1, will be given here. Yeah. So once we have 3, 3 just means that 1 remainder 1, right? So the sum will be 1, and then the carry will be 1. So this is how you get the truth table of your full adder. So now, how do we first of all implement this full adder using our PLA? We have to first of all look through how many outputs do we have in our truth table. We have only two outputs, the carry and the sum. So what will happen is that we have to disconnect one of the outputs. Here, this PLA has 3 outputs, X, Y, Z. So we have to disconnect one of them and then use only 2 outputs. So all the connections to this one will be deactivated, right? So will be turned off. So that is the first thing you do. So here we have cut off this portion, or all the inputs to X will be left out, and then we just assign our C, our carry here, and then our sum here, and then we have our A, B, C. So now, how do we know that this works correctly? So let's check our first the first carry the first carry in. Now if A is 0, B is 0, and then our carry in is 0, we know that our carry out here will be a 0. So we have to trace here. So we have A, B, C, and then this is the connection to the carry in, right? Okay, so now if you want to trace the carry the carry out, we have to first look through the truth table for the carry out and see where there is a 1. So we see that there are 4 ones here, 1 here, 1 here, 1 here, and 1 here, 1 here, 1 here, 1 here, and 1 here. And then those are the connections you have to make, right? So this see out the 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 output of the carry has the output of the carry, which is this all gates here, has 4 inputs, 1, 2, 3, 4, and this will be indicated in the truth table, 1, 2, 3, 4. And now the inputs to this um, all gates are the outputs from the AND gates, right? So for the first one, if you look at the first one here, which is this one, our A is 0, B is 1, our carry in is 1. So just look through here. So you see that A is 0, B is 1, and then our carry in is 1. For the next one is here. A is 0, A is 1, B is 0, C is 1. So it's this one here. So A is 1, B is 0, C is 1. So once you look through the truth table, you see that we have A is 1, B is 0, and C is 1. So you can trace that, and then you will see and make all those connections. And then this is how you implement a full adder using the PLA, the programmable logic array. Right. Now let's look at a comparator. The comparator is also another digital circuit component, a very, very important one. It's just a comparator is just an equality checker. It compares if 2 bits are equal. So now if you have so let's see which logic gate can be used to compare if 2 bits are equal. So let's take we have input A, right? We have our output Y. We are comparing 2 bits, so we have input A, B, and then our output Y, right? So we want to compare if A is equal to B. So 0, 0, 0, 1, 1, 0, 1, 1. Yeah. So if A is equal to B, the value of Y, the value of the output is 1. So A is 0, B is 0, so the output is 1. Right. Now if A is 0 and B is 1, they are not equal, so the output is a 0. If A is 1, B is 0, the output, they are not equal, so the output is 0. If A is 1 and B is 1, they're equal, so we have a 1 here. So this is the truth table of a 1-bit comparator. Compares A and B, which 1 bit. A is 1 bit, B is 1 bit, so we'll be able to compare it. So which logic gate mimics this? So this is a simple So which logic gates actually mimic this? So if you take an exclusive OR, right? If A for exclusive OR gates, if A is 0, you have a 0 here, you have a 0 here. If any of them are different. We have a one here. Now, if we invert the output of the exclusive NOR, so not XOR, we are just inverting this one. So here will be 1 0 0 1. So it means that this logic gate, the XNOR, is what will be used to do comparison, and then the XNOR has a symbol, as you already know of this. So this is A, and then this is B, and then this is Y. So this is a simple comparator. The XNOR can be used as a comparator for just one bit. So if you have several bits, then you can use several of the XNOR and then route your inputs to them, and then you get an output, right? So this is the symbol for a comparator, which is equal. So here we have, if you have 4 bits A, 4 bits B, we have an equal sign here, and then we just compare. If A and B are equal, the output will be a 1. If A and B are not equal, the output is a 0. And then we can only do this using 4 exclusive NORs here. So 4 of these ones will be used to do that, and then we route all of the inputs to an AND gate, and then the AND gate will give a 1 if all the inputs are the same, and then it will give a 0 if even one bit of the input is different. So this is what is called the comparator. Now we also in our single cycle processor, we'll be designing what an arithmetic logic unit looks like. The arithmetic logic unit is just comprises of arithmetic operations, the addition, subtraction, probably division, multiplication, and operators like that. And in addition, it also has logic units, which comprise of an OR gate, AND gate, XOR gate. So all of this can be designed using combinational logic. And then one of your assignments would be on designing an ALU using a variety of gates, AND gate, OR gate, multiplex decoders, right? So I won't go too deep into it. You'll be doing it as an assignment. Now, a very important logic gate is the tri-state buffer. It's just a single gate, and then the tri-state buffer will actually enable an an out an input to be routed to the output, or it leaves the output floating, right? So first of all, in terms of all the logic gates we've looked at, if you look at the AND gate, the OR gate, the XOR gate, there's always a value at the output, right? The output always has a value. For instance, if you take an AND gate, you have Y here, you have A, B here. The output will have a value of either 1 or a 0, right? So every time there is a value that is assigned to the output. But then we have another logic gate, which is the tri-state buffer. Tri-state buffer. This is the symbol for the tri-state buffer. It's a buffer, and then we have an enable, so E here, and then we have A and Y here. Now what happens is that anytime the enable is a 0, right, the value of A is cut off from Y. So we say that the value Y is floating, right? Or the value Y is has a high impedance. High impedance, right? So A is floating, or A is at high impedance. It means that the output is not connected to any wire at all. It's not connected to the input at all. So it's just floating, or it's at the high impedance. So the truth table of the inverter is seen on the slide. So as long as as long as E is 0, the output is floating. Now the symbol for high impedance of floating is Z. So now it's no longer, it's not a 1, it's not a 0, it's Z. Once you say Z, it means that the output is floating, or it is at high impedance. So anytime the enable is 0, the output floats. So you see here we have 0 here. Even though the input is 0 or 1, the output is a high impedance or is floating. Now when E is enabled, then the output will be routed to then the input will be routed to the output, right? So if E is 1 and then the A is 0, the output is 0. If E is 1 and then A is 1, the output is a 1. So this is what is known as the tri-state buffer. Now, the tri-state buffer has so many uses in digital logic design, right? One of the uses is that you could have um, two components, right? You could have two components. For instance, we in the digital system we have what is known as the shared bus. The shared bus, and then all components within that system is connected to the shared bus. So if we are designing a CPU, our CPU will be connected to the shared bus, right? And then the CPU will have to access memory. So the memory is also connected to the shared bus. But the issue is that the CPU and then the memory cannot use the shared bus at the same time. Even though it's shared, only one can have access to the bus, and then the other one must be deactivated. So if the CPU needs to use the bus, the CPU will have to enable a component on its side to be able to use the bus, and then the memory, the components on that memory will have to be deactivated. So here, what we can do is we can connect the tri-state buffer to these two components. So we have our tri-state buffer here, and then we have a tri-state buffer connected here with our enable, So if the CPU wants to use the bus, it will have to enable its tri-state buffer, and then its value or whatever data it has will be sent to the shared bus. If the memory wants to use the shared bus, it will have to enable its tri-state buffer, and then the values or the data within the memory will be sent to the shared bus. So that is one use of the tri-state buffer. And then we have a number of components within the present system. All the components will be connected to a shared bus and will be connected to a tri-state buffer before they are actually connected to the shared bus. Right. So now we can also use our tri-state buffers to actually design um, multiplexers. So you can go through it and see how it is done. And then the most important thing here is that comparing the design of a multiplexer. This is a 4-input multiplexer connected to a 1 output. So you see that you can easily use 4 tri-state buffers to design it. And then once you go through once you go through the design of a multiplexer using AND gates and OR gates, you see that you are using more gates. You're using a lot of gates, and then once you're using a lot of gates, you're using more transistors when you're using AND gates and OR gates to design a multiplexer. But when you're using a tri-state buffer, the number of transistors are less. So you have to, as a designer, you have to know this kind of configuration to know that a particular gate that you are using will have less number of transistors as compared to another logic gate. Right. Now let's talk about the last component, which is the priority encoder. Now we have in hardware design components again. Oh yeah, I shouldn't have cleaned this. components are always connected to a shared bus. As I said, we have a shared bus, and then we have components connected to the shared bus. We have again, we have our CPU connected to the shared bus. We have memory connected to the shared bus, and then we have other components like the input output will be connected to the shared bus. We have some input output peripherals will be connected to the shared bus. Then we have maybe probably some hardware accelerators will be connected to a shared bus, right? All of these are using the bus, but they cannot use the bus at the same time. One has to use the bus, and then all the rest will have to stay idle for a period of time before the one that is using the bus finishes using the bus. Now here we have what is called how do we assign the buses, or how do we assign the buses? First of all, each component has to request to use the bus. So if CPU wants to use the bus, CPU will send a request signal that I want to use the bus. If memory wants to use the bus, memory will send a request signal. If IO wants to use the bus, it sends a request signal. This request signal is just one bit, just one bit request signals, right? So it means that if CPU wants to request the bus, it has a line that connects to the bus in which it's just one bit, and then it will just activate that line to one, right? CPU wants to use the bus, so it just makes that signal one. If it doesn't want to use the bus, it will make it zero. Same with the others. So a component requests to use the bus, and then the bus has a circuit within it that will assign that will assign so here CPU request for the bus, and then the shared bus will also have a signal called the grant signal, and then that will, if the grant signal is 1, it means that CPU can use the bus. If the grant signal is 0, it means that CPU cannot use the bus. So all the components have a request signal, and then they will receive a grant signal from the bus. The IO also has a request signal. We receive a grant signal from the bus. The accelerators have a request, grant. Accelerators have request, and then they receive a grant signal. So these are all just one bit, one bit, one bit. So we have a grant and then the request. So now what happens is that one method that the shared bus uses to assign or to grant the bus to each component is the priority, right? So now before the shared bus grant the opportunity to any of the components to use the bus, it will have to look at the priority of the components. So first of all, the components have to assign some kind of priority. So let's say if there are 4 components, let's use 3 to be the highest priority. So we can assign CPU to be 3. So it means that CPU has the highest priority, followed by memory. So memory has a priority of 2, followed by IO 1, and then followed by accelerator 0. So anytime CPU requests to use the bus, the bus will look at the priority of the CPU. If the priority of the CPU is 3, it will immediately grant the bus to the CPU. Now, what happens if CPU and memory request the bus at the same time? What happens is that if CPU requests the bus, memory also requests the bus will look at the priorities. CPU is 3, memory is 2. So immediately the shared bus will grant or will make sure that the CPU uses the bus. before the memory uses the bus. So this is what we use a priority circuit for. The priority circuit will be within the the shared bus that will grant, or that will actually give access to one of the components, and then leave the other idle. The others cannot use the component as long as um, a component with a higher priority comes in. Once a component with a higher priority comes in, all the other components are deactivated from the line, right? So this is how a priority circuit looks like. If you see this symbol, that is just a priority kind of circuit, right? So here we have our input, which is A0, A1, A2, A3. The inputs are the request. So here A0 is a request line, A2 is a request line, as I said, request. A1 is a request line, A0 is a request line, and then the output Y1, Y2, Y3, and Y0 are the grant lines. So that is the from the shared bus, the shared bus granted. So um, if Y3 is 1, means that the shared bus has given the opportunity for um, A3 to use the bus, right? If A1 sends a request and then Y1 is 1, it means that the, the shared bus or whatever component it has given access for A2 to use the bus. So now we have, this is the truth table of our priority circuit. So here, once you study the truth table, you can easily see that as long as A3 is 1, so let's look through the truth table. If A3 is 1, the grant line is 1. We don't care about A2, A1, A0. As long as A3 is 1, the grant Y3 is 1. So it means that A3 has the highest priority here, because as long as A3 is 1, all the other inputs are ignored, and then the grant line is given to Y3. Next, if you look at A2, when A0, when A3 is 0 and then A2 is 1, here again Y2 is 1 and then the rest are zeros, right? So Y2 is 1 and then the rest are zeros. So it means that the next priority is A2. Now we move on to A1. As long as A3 and A2 are zeros and then A1 is 1, the next priority or the next grant signal will be Y1. Y1 will be activated, and then it means that that is the one with the next priority, and then the one with the lowest priority, if A0 is 1 and all the others are zeros, that is the only time A1 gets Y0 gets activated. So it means that A0 has the lowest priority and A3 has the highest priority. Now, how do we design, or how do we use logic gates to actually implement this circuit? So let's see how we can use AND gates, OR gates, or whatever gates we have to implement that logic. Okay, so we can first of all start with A3. Okay, now let's start with A3. Our input is A3. Now our output is Y3. So here, as long as A3 is 1, our Y3 is 1. Right, so A3 does not depend on A2, A1, and A0. Once A3 is 1, Y3 is 1. It doesn't depend on anything else. Now let's look at the next one. It's our A2, right? And then we have our Y2, right? So now once we look at through the circuit, we have to make sure that A2 depends on A3, right? So we need an AND gate here. We have A2 here. So if A2 is 1, it actually depends on A3, right? So we have to connect A3. We have to connect A3 here. But then we have to use an inverter here. Or for some, just use a circle here to indicate. So now what this means is that if A3 is 1 and A0 is 1, what happens? Y3 is a direct line, there's no connection to it. So 1, and then A3 being 1 here makes the output of the inverter 0. So the output here will be 0. So if A3 is 1 and Y3 is 1, Y3 is 1 and then Y2 is 0. Okay, now the only time Y2 will be activated is if A3 is 0 and A2 is 1. So if A3 is 0, Y3 is 0, and then if A3 is 0, the output of the inverter here is a 1, and then if we have a 1 here, the output is a 1. So that is the only time A2 gets activated, right? So this circuit is right for A3 and A2. So you have to now look at Y1. So our next is Y1. Okay, so for Y1, it depends on, so A1 is 1, and then it depends on both A3 and A2, right? So if A1 is 1 and then A2 is A2 is 0 and then A3 is 0, that's the only time Y1 gets activated, right? So the last one is Y0. So we know that Y0 depends on A0, and then if A0 is 1, you have to actually check A1, A2, and A3 to be zeros before Y3 can be activated. So before Y0 can be activated. So Y0 depends on A3 to be 0, A2 to be 0, A1 to be 0, and then A0 to be 1 before Y0 can be activated. So this is the simple circuit for a priority circuit, and then we are using just inverters and an AND gate, right? So this is the end of the combinational logic lecture. Thank you.